Okay. Sorry about that, folks. There was an issue with the mic there. I'm not sure why it did that, but it shut out. So hopefully you can all hear me now. All right. Apologies. This is this is ridiculously complicated technology. It should be so easy, and there's just so many freaking things to think about. Anyway, thank you for tolerating all this. All right. So as I was saying, marking. You should be getting your assignment marked now. Your tutors. You've got a fantastic set of tutors. You can see them all on your webpage. You've hopefully met them at least virtually. But your tutors aren't magic, okay? They're working really hard, but they're also, all of your tutors are also students, and they're all students who did really well in this course. Now, so they've got other commitments, and as many of you will appreciate, right now, a lot of us have extraordinary stresses placed upon us due to the circumstances. So please be patient with your tutors. Your tutors are doing their best to get the marks to you by the end of this week. But circumstances will be such that some of them may not be able to, okay? So if that's the case, please be patient and please be understanding, all right? Anyway, well, you can ask, if you don't get your mark by the end of the week and your tutor hasn't said anything to you, you might politely ask them in a private message on Piazza, okay? But the goal is that they'll have your marks to you within a week, all right? And the way you get your marks is, well, you'll see the mark on streams, and also when you do a pull, when you do a pull on GitLab for your assignment 1, you'll get a new file there called feedback.md, which will have all of your marks in there. It'll have your auto grade marks, and it'll also have the marks that your tutor gave. All right. Really cool thing for Friday. We're going to have a guest lecture. This guest lecture is one of the great things, one of the lucky things that you have going to a university like ANU is you get some access to some fantastic people. Your guest lecturer on Friday is Pascal Bircher, and he is an expert on AI. He's internationally renowned expert on AI, and his particular expertise is in the area of planning and optimization. This is a really important area of AI. It's used, for example, in robotics, planning a route for a robot and this sort of stuff, or planning. They do all kinds of interesting stuff to do with power management, like as in the electricity grid. They do work with. I know that they've had a contract with Airbus on how you can plan routes for airplanes to maximize fuel efficiency, and doing crazy stuff like having convoys of airplanes so that they can be the ones behind can be more efficient than the one in the front. This kinds of crazy stuff. So it's got a lot of real world applications, and it's an area called planning and optimization. Now Pascal's lecture is going to be focused on the fundamentals of AI, and will take a specific tilt towards the COMP1110 assignment 2, which involves building an agent to play a game. Everyone is invited to the lecture. Those who are in 1140, the content of the lecture is examinable just like any other lecture. If you're not in 1140, that particular lecture is not examinable. Okay, so the content of Friday's lecture is examinable for 1140, but not for other students. Everyone is invited and encouraged to go. The way it's going to work is I'm going to have a Zoom session here with him. His slides get presented here. They'll come streaming just like, from your point of view, nothing will change. You'll just get a streamed lecture just like normal, okay? But what I'll be doing is I will be looking on the chat on Teams to take your questions there, and then I'll put your questions to Pascal orally. So I'll frame your questions and ask them to Pascal. So it's really important when we have guest lectures in this class that you use that to ask great questions, okay? So please get ready for Friday to ask great questions to Pascal. They can be broad brush ones like why do you like AI, or what's the future of AI, or they can be very specific ones like how do you think we're going to do X or Y in assignment 2. Any of the above, whatever you like. But please, I really like it when my class engages with guests. I get really good guests for you guys, and I really want you to engage with them. Okay, we've got another phenomenal guest coming up very soon. I think next week, the week after this one, we've got another amazing guest. And I'll talk more about her later. But that's all I want to say about Friday. Assignment 2, all being well, will be released tomorrow morning, and so you'll all get to see that. The important thing about assignment 2 is it's a group assignment, unlike assignment 1. And so you'll be put into groups. The groups they're randomized groups. Randomized groups of 3. Everyone's in a group of 3 unless you're in a class group that has an odd number or something that doesn't divide by 3. and so you might be in a group of 2. But pretty well everyone will be in a group of 3. The other 2 people in your group will be random, and some of you are thinking, oh my god, I could be stuck in a group with a complete jerk. Unfortunately, that's absolutely true. But this is the real world. This is how the world works, and one of the big challenges of this assignment is not the technical dimension, but the social dimension. Okay, don't underestimate that. That's actually a key part of it, and that's actually part of what this course is about. Okay, so this course is not about learning Java. I've said that to you lots of times. It's not about learning Java. We're going to use Java. We're not going to learn Java. You need to learn Java in your own time. I've tried to give you the scaffolding for that, but it's about using Java to build software, and you also need to use social skills to build software. So a lot of this is going to be please no jerks. Yeah, that's exactly right. We don't want jerks in our class, and we do not want jerks in your group, and you want a great group. And I'm going to get in today's lecture, I'm going to talk to you a little bit about how you make that work. All right, but some of you are probably thinking, oh, this is horrible, I wish I could choose my own group. And I get that. I totally get that, right? But that's not how we're going to do it. We're going to do it with randomized groups, which is actually a lot more like what happens in the real world. In the real world, your boss says, hey, you're working with Fred and Mary today, and you're going to do this thing, or for the next year, you're going to be working with Fred and Mary. And you just got to work out how to work with those personalities, work out where their strengths are, work out where their weaknesses are, and work out how to manage that. We're going to try and provide as much scaffolding as we can to make that work as smoothly as possible. And obviously, there are interesting challenges associated with you all being virtual. But that's how it works. I want to set that up for you. And no, you can't go and be in a group with your buddy. If you happen to draw the dice falls nicely for you and you're with your buddy, well, good luck. But the odds of that are pretty slim because we've got a large class in the randomized groups. All right. How can you find the marks of your assignment? Yeah, on streams. That's right. Basic competency test, the last piece of admin. Remember, this week, if you did not pass the lab test, or if you have an oral for the lab test and that goes to 0, some people are going to get oral exams for the lab test. They're kind of random, so don't be afraid. If you get an oral exam, don't stress, okay? So what's going to happen in the oral exam is I will examine you, and I will do that at the start of your lab. And if I examine you and it all looks good, then your lab test mark just will stand as it was. If it doesn't look good, then your lab test mark could go to 0, okay? Now, if that happens, then you'll have to take the basic competency test along with everyone else who got a 0 in the lab test, okay? And that basic competency test is just that. Shouldn't be too stressful for you. If you've done any of the background work, you should be able to get through that. However, you do need to pass it. If you don't pass it, as the webpage explains very clearly, you're out of the course, all right? All right. Is the audio out of sync? I hope it's not. So, all right. Let's move on. I think we're ready to move on to the rest of the lecture. Where are we? Yeah. Last lecture on Friday, we started with JavaFX. We did the first module of JavaFX. Now we're going to do the second module of JavaFX. In the last lecture, what we did in JavaFX was look at how you can put a window up. If you remember that, we did hello world in a little window. We did a red square in a window. And then I showed you some very basic tricks like how you can do opacity, change the color of the square, or change the color of the text and that sort of stuff. And you'll also remember that sometimes debugging JavaFX can be hard because it's a visual medium, okay? It's a visual medium, which means that if you watch the lecture, you'll know that I thought that there was nothing in the window, but actually the color I chose, which was azure, right? Azure, the particular color actually renders almost like white. So there was text on the screen. I just didn't notice it initially. Okay, that's a good example of how debugging JavaFX can be tricky because it is actually visual debugging, not just regular code debugging. All right. The key thing I'm going to do in today's module, the X2, is talk about event handling. This is a very cool idea and it's a really interesting concept, and it's absolutely relevant to doing a graphical user interface. How does event handling work? Well, hopefully you can all remember what are the 3 key things of control flow things that we have with imperative programming. Can anyone remember what the 3 things for imperative programming were? I gave you 3 examples, and the first one was was a sequence, right? Sequence. So you do one line of code after the next. That's the very first thing you did in lecture 1. Selection is when you get to choose, do I go this way or do I go that way? And that's with a branch. And iteration, yeah, that's right. Iteration is when we go in loops. And then, so that's sequence, section, and selection and iteration. And then we talked about methods, okay? I showed you how we can call a method, That's another way you can change the control flow. So you're going along here and suddenly you go out there and you do a method, you do a piece of code or a function or a procedure. They're different words for the same idea. That is a bunch of code that you go and do and then you return back to where you were. That's a method. In Java we call that a method. In other languages you might call it a function, you might call it a procedure, but it's a chunk of code that you go to and then you return back to where you left off. Okay? And we use what's called the stack, and you sell that with a Waterloo visualizer to keep track of where you were and where you come back to with a method. Events are a completely different kind of control flow. And the idea of the event is that when you have something like when you have some environment, some software environment, when something happens, do a particular thing. So something in the background is monitoring, and then when it sees a particular event happen, it executes a piece of code. So instead of branching to a piece of code or looping over a piece of code or calling a method, it actually spontaneously, if you like, spontaneously executes a piece of code on the basis that some event occurred. Now, why would you want to do this in a GUI? Can anyone think of an example of when you'd want to handle an event in a GUI, in a visual application? Anyone think? The obvious one is something like a mouse click. Okay, someone clicks the mouse. What you don't want is you have your program continuously saying, hey, has the mouse been clicked? Hey, has the mouse been clicked? Like that would not be a good way to do it. Instead, what you really want to do is you say, hey, when the mouse gets clicked, please do this thing. Okay, so you say, please do this thing when the mouse gets clicked, and then there's some other thing in the background that's looking for a mouse click, and when the mouse click, if and when the mouse click happens, it goes and does that thing. Okay, so that's a great example of an event, and you can do it with a key press or whatever. Okay, later on, not yet, but later on in this semester, we're going to talk about exceptions. And exception handling is a thing that many programming languages have, which is actually quite closely coupled with the idea of events. Okay, what they have in common is that you're executing code and spontaneously execution goes somewhere else. In the case of event handling in a GUI, the spontaneous trigger is something like a mouse press. So instead of doing this, suddenly you're over here doing that. Exception handling has a similar sort of behavior. So it's complete deviation from the standard control flow that I spent a bit of time explaining to you. So you get this notion of control flow, which goes through sequence, selection, and iteration methods. And then you've got this idea that something happens and bang, you're executing code elsewhere, and then you return back to where you left off. Okay, that's the idea. Events and passing code in Java. So how do you, if what we want to do is say, when this event happens, execute this particular code, how do we express that code? I'll give you a clue. I taught you this just last week. What would we do? How would we express the behavior that we want to have happen when a mouse gets pressed? Okay, and the question on the slide there is, how do I pass code as an argument in Java? Because that's essentially what I want to do. I want to say, hey, when the button gets pressed, do this thing. Yeah, we want to pass a lambda. Okay, we want to pass a lambda. So we pass a lambda, which is a piece of code, and say, look, when a button gets pressed, do this stuff, and the stuff is a piece of code. Okay, and in Java we call that a lambda. Okay, so it's a lambda. A lambda is a piece of code, and we say when this occurs, do this piece of code. All right, and so lambda expressions. All right, and we covered that in unit J09. So events in JavaFX. JavaFX has got its own little framework for doing events, and so whenever you get an event, it is of type event, and it could be a subtype of event. So so it typically will be. For example, here. We'll see in a minute different types of events. So what do you get when an event happens? You get the type of event, which could be a key press or a button press, or it could be a mouse drag, it could be all kinds of stuff. The source of it and the target of it. And the source and the target refer to where in the scene graph. And that, we're not going to deal with that right now, but it's quite useful because it means you can pass things on. The way it works, the way JavaFX works, is remember that the objects in the graph, it's a scene graph, like a rectangle, and inside the rectangle might be something else and so forth, and they're grouped. And what happens is the thing that's closest to where the event happens, like where the mouse gets clicked, gets the opportunity to handle the event. If it doesn't handle it, then the thing that contains that gets to handle it, and eventually the scene gets to handle it. Okay, so you have this cascading of handling where you're starting at the most specific thing and ending up to the most general thing, and each one of them has the opportunity to deal with this event, like the key got typed or the mouse got clicked. Okay, so the principle there is, let's give the event to the thing that seems to need it, and if they don't handle it, then hand it to the thing that contains that thing, and so forth, and eventually you get to the window. All right, so that's how it works. All right, there's a little mini quiz here. I'll just publish that. and let's get on with writing some code. All right. Here's, oops, I forgot to close all this stuff off from Friday. There we go. We'll close some of these little files off, and I will remind you of what we did at the end of last lecture. We did a hello world, and we did the square. So here's the square. Let's just run that. Here, let's run the square. Run. So that we did that. Okay, so that was a window with a title up there which says square. There it is, and a red square in it. And then we did hello world. Run hello world. And what we did is we messed around with things like changing the opacity of the text. So we changed the text so it was slightly opaque. And then we changed the opacity of the thing called the stage. Remember, the stage is JavaFX's way of referring to the window in your operating system. So the whole window is now opaque, so you can kind of see through it, okay? And by changing that number there, we could change the opacity of the window. That's what we did on Friday. And we're going to build upon that stuff right now, creating a new module here. New Java class, and we're going to call it JavaFX key event x02.javafx JavaFX key event. All right. Now I'm going to cut and paste some code, but I'm going to start off by doing this explicitly just to remind you of what we do. What's the first thing we do when we create a class in JavaFX? There's one thing we need to do. All JavaFX classes need to do something. They need to extend application like that. Extends, plural. Okay, extends application, and then asks us which one we want, and we want that one. So we press the appropriate keys to get that to happen. We import the class. There it is. Which one do we want? That one. That's the one we want. Perfect. Okay, so we've now extending that. Now we've got a red light bulb. What's that going to say? It's going to say, hey, you haven't implemented the methods. And so we'll say, sure, please do that for me. So IntelliJ is going to put those methods in for us. We could have just typed all this in, but IntelliJ is trying to be helpful and say, hey, it's an abstract class. Application is an abstract class. And if you want to extend it, you probably want to implement the methods. And the method that you need to, the abstract method you need to implement is the one called start. Okay, so that's just boilerplate. Everything I just did so far is boilerplate. You should know you're not going to be examined on this. Remember, I'm not going to give you a coding question in an exam where you actually have to type all this stuff in, but you will be writing exercises in class and you will be doing it in your assignments. So you might find it useful to remember how to do this. And then what we have to do some basic stuff here. We're going to remember the stage is the operating system window. That was the little window that we saw on the screen. And the first thing we're going to do is change the title of that. So stage dot set title. Oops, not set opacity. We don't want to do that. Set title like that. And we'll call it key press. Okay. And then there's a whole bunch of stuff here. I'm just going to pinch stuff from the previous lecture to save typing all this stuff in. Here we are, pinch it from Hello World. We'll just grab that whole lot. I'll walk you through it in a moment so you don't, so you get to see what all this stuff does. Get rid of this. Okay, so now let's just walk through this. So we've set the title of the window to key press, so which means at the top of the window, like here it says COMP1110 lectures, it's going to say key press, okay? Then we've made this thing here, which is the container for all of the stuff. We use this particular one. I explained this in the last lecture. If you go back to the lecture, you can see why I did this. This particular thing is a nice way of arranging text. That's just a nice way of arranging text. It automatically centers stuff for you. That's all this stack pane does, okay? And this is going to be the container in which we put our text. Okay, we create a scene. Remember, the metaphor is you've got a stage, which is the window, and a scene is something temporarily you put in there. And the scene is going to be of this size here. It's going to be 300 by 300, and it's going to have this stuff in it. Okay, that's the content of the scene, and it's a stack pane, which currently is empty, of course. Okay, then we've said to the stage up here, we said stage, please make this the scene that's going to be on display. So we've put that past that and said set that as the scene. Okay, then we've created some text, and the text says hello world, and we've set the font to a particular font. We've given it a particular weight. You can do all this sort of stuff, change it to a particular font, and then we've changed the color. We'll change that to regular or something because I think that'll be too big to fit on our screen if I remember rightly. Medium, all right, or normal. How about that? You can mess with all this stuff, mess around with it to make it look the way you want. We've set the color of the font to be red. We don't need to change the opacity. I was just doing that in the last lecture to show you how it worked. And if we run this, we should see we should see something very simple, nothing very exciting here, because I haven't really done anything interesting yet. That was essentially just revision on how to... Okay, so now we have a window. Notice the title of the window is key press, which is what we set up here. And it's got the words hello world, which is this text here. And it's displayed in the middle. It's in the middle because we use this stack pane thing here, which is a way of structuring the content of the window in a way that centers it. All right? That's all. And everything I just did there is stuff I covered in the last lecture in Unit X01. Now comes the new stuff. What we want to do is... oops, put that up there. I put the line break in the wrong place. Okay, so one last thing. I'll just repeat one thing from the last lecture that I know people get confused by. This stuff here creates the text, but here what we do is you say, get the children of this root and add the text to the set of things in there, which basically means put the text I created into the container. And if you don't do that, then you get nothing displaying, right? Because it displays nothing because it's not inside the set of things that are going in the scene, all right? That's very important. Yeah, you can. James asked about what about using an action listener. There are many ways of doing it. I'm using lambdas here because that's one way of doing it, and it ties in with a more core computer science that we're teaching the class about what a lambda is. So yeah, you'll find with JavaFX there's a bazillion ways of doing so many things. I'm showing you one way of doing it, and it's intentionally fairly simplistic. But if you really like this sort of stuff, you can go and read to your heart's content. There's some really rich tutorials. I've got links on the web pages for these tutorials for JavaFX. You can completely go to town if you want to do something elaborate. But what I'm showing in the lectures is kind of minimalistic, and it's what I really want you to understand. And what I'm really trying to show you here, folks, is the concept of event handling, because that's a core computer science concept which manifests in many different languages and many different ways. And JavaFX has a particular way of doing that, and we can do that using a lambda, which is a concept I just taught you. All right, so let's get on with this. So what we're going to do is we're going to add a handler to our scene. So scene, there it is, scene dot set on key typed. Now notice when I get the autocomplete here for IntelliJ, it's giving me 3 options. And see if you can imagine what the difference is between pressed and typed. It's subtle, right? It's really subtle. Typed is the language they use here to describe the action of pressing and releasing. Okay, so when I hit a key like that, I hit the shift key. That's pressing and releasing. Okay, which corresponds to typing. Okay, so what if you say set on key typed? It means don't tell me about it until the person has pressed and released. Okay, by contrast, pressed and released allows us to know then it's pressed and then it's released. Okay, depending on what you're trying to do, usually or very often all you want to know is did someone type the A key, did someone type the B key? But sometimes if it's controlling a game or something, you want to know is someone holding down the shift key like I'm doing right now on my computer, or holding down the left arrow key like I'm doing now, or holding down the right arrow key like I'm doing now. Okay, so that's the difference between typing, which is press and release, pressing and releasing. Okay. All right, so people have got issues with Twitch. If other people are successfully watching on Twitch, that would help me to know that. I can see it on Twitch over there on my screen, and it looks okay, so maybe it's a local issue. All right, so what we're going to do here is going to say set on key typed. Okay, and what we need to do now is pass in the event handler, and what we're going to do is we're going to say the argument we're going to get is an event. Right, it's a lambda, okay, and it's going to be event, and it says, hey, it's actually a key event because key typed means a key event. That's one of the kinds of events. We could have just called the variable event if we want to, but IntelliJ says, hey, why don't you call it key event, okay? All right, and then what we're going to do is we've got to write our code, right? So that's the argument, that's like a parameter that comes in, and then we're going to write our code. And what we're going to do is something very, very simple. We're going to change the text according to what got typed. Okay, so we're going to say hi.setText. Right, hi was our text up here, right? That thing, it says hello world. We're going to change it to write something else according to what got pressed. So we'll do this. You pressed R, and then we'll put it. Whoops, hang on. You pressed A, and I'll use a single quote there, and then I'll put in the value that they pressed. So when they press a key, I'll put the value in there. And the way you do that is you get the value from the event. Key event dot get character, and then I'll put another little close quotey thing there, and we're done. Now let's see what happens. So what this is doing, this is saying, for my scene, add on a new event handler, which happens whenever a key is typed. And what we want to do is we give it this lambda, which says, okay, take the key event, and when you get this thing happening, change the text of the high text up here to say this. Okay, so each time we press the key, it should change. Now let's have a look at it. All right, there it is. I haven't pressed anything yet. Now let me press the D key. Okay, you press the D. Now if I press a whole bunch of different keys like that, you can see it's changing. All right, so, and if I press the Shift Q, I get an uppercase Q, lowercase q, uppercase Q. Okay, very, very simple code, but what's happening is each time I press something, an event happens, that goes and executes my little bit of code over here, and that changes the contents of our little text thing to say this, okay? Now, one last thing we can do is we can do something which we often do want to do. In fact, if you look at your assignment 1 GUI, you'll see this code like this. You can say key event.getCharacter. If key event.getCharacter equals, and then we'll say Q, uppercase Q, then let's quit. Okay, so what we're going to do is we're going to say if someone pressed the uppercase Q, then let's quit the program. Okay. Otherwise, we'll do what I said there. Okay. Otherwise, we'll update the text. Okay. So, and then the way you exit the program is a little bit weird in JavaFX, and the reason why it's weird is because under the hood something interesting is happening. It's actually running what we call threads, multiple threads. We cover threads later in semester. You don't need to know that, but what you do need to know is you have to exit a special way. You do it this way: platform.exit. You call this, okay? That's the way you exit in JavaFX, and that's a useful thing to know. And so what we're going to do now is we run this. It should be just like before, except when I type an uppercase Q, it should do this, which should stop the program. Okay? Okay, like this. And someone said, yeah. All right, so now what I'm going to press the uppercase Q like this, and it's gone. Whoops, something didn't finish nicely. I don't know what that was. Okay, it didn't behave completely nicely, but it quit, right? It quit when I hit the uppercase Q. There it is, like that. Okay, so it quit. Not quite sure why it was so ugly. I'll have to look at that later. It doesn't normally do that. Okay, anyway, that's the way you're supposed to exit. And you've finished learning about event handling. And let me just quickly recap here. We've got a basic piece of code here, which is just like our hello world. All we added today was this little thing here, which is an event handler, which said that whenever a key is typed, do the following stuff. And it says, take an argument, which is the event that happened, then get the character out of that event. So an event happened, inside of it's a character. And if what happened was a queue, then exit, otherwise change the text. All right, and with that, we're ready to move on. Right, next we're on to revision control, okay? Revision control is something you've already been exposed to, obviously, but we're gradually learning more and more about it. Okay, in Lab 1, you had to do Hello World. And when you did Hello World, we walked you through this mechanically. You weren't supposed to really deeply understand it. You need to know the mechanics of how it worked. Gradually, we're giving you more and more information. You do this all the time in real life. When you go to the ATM at the bank, you don't necessarily know how it all works inside, but you know the basic functionality. When you do things like this, the money comes out or the money goes in or whatever it is, okay? You understand the mechanics of how it works, even if you don't understand under the hood what's going on, all right? Now we're slowly peeling back the layers and looking more at what's going on. This is a really crucial thing, and in this course we use Git. Why do we use Git? Someone asked a question before about why we use Java rather than C#. Why do you use Git rather than Mercurial? Not a strong reason, just pragmatics. In this class, the way I do things is I try to use tools that are freely available on as many platforms as possible, preferably Linux, Mac OS, and Windows, okay? And B, I want ones that are open, so you guys don't have to pay money to use these tools. And crucially, I want ones that are really widely used in industry, okay? So that you're not using toys, you're using the real thing, Okay, there's some of the key criteria, and above all, that they're very well documented. There's tons and tons of stuff on describing how these things work all over the place. There's tons of stuff on how Git works. There's YouTube videos everywhere. There's loads and loads of information on these tools. That's a philosophy I have in this course because it's about software construction, and I want you guys to become familiar with key tools that we actually use in the real world. Okay. So let's now move on to some key Git concepts. And there's a little funny check mark there against things that hopefully you're already using. You may not use the update command, but that's the commit and push and pull you should be thoroughly familiar with now. And there's two different uses of the word commit, slightly confusingly perhaps. There's the verb to commit your work, but there's also commit, meaning a particular revision. Okay. And there's this notion of staging, which says I'm going to commit. These are the files that I want to commit soon. Okay, and you stage them and get ready to commit them. Depending on how you use IntelliJ or depending on how you use Git, you may not even notice that. Okay, so now let's go into these a little bit. What is a Git commit? Now I'm talking about the noun. A commit is a thing. It's like a transaction when you go to the bank. It captures a set of changes that may span multiple files. Now this might seem obvious to you, but it's actually not so obvious to many people because other revision control systems don't do that. Okay, older ones didn't do that. With other ones, you could only, a commit was against a single file. There's an enormous advantage to being able to capture the set of changes to a whole set of files. What this means is, I took the system, I took my repo, it's in a particular state, and I made changes all over the place. Now I'm doing one commit, which covers all of those changes I made, even if some are in that file, some are in that file, and some are in that file. The alternative might be to have to commit each one at a time, okay, each file separately. Now, I'm just looking, people are having issues with Twitch. But presumably some people are not having issues with Twitch, and if people are not having issues with Twitch, that would suggest the problems at your end, unfortunately, not mine. Because if some are getting it through clearly, then that means it's reaching Twitch just fine. Yeah, and YouTube's fine too. All right, Twitch is fine for some people. So that suggests that some people in some locations, Twitch is misbehaving, which is unfortunately nothing I can do about that. It's reaching other people just fine, so that must mean it's a downstream issue, or maybe something local to your computer. Maybe there's a network issue near your computer. Okay, but the fact that some people are seeing it fine on Twitch and YouTube suggests that it's fine. And if it's only on and off, then again it seems like it's an issue with Twitch, because some people are seeing it fine on YouTube. And the way this system works is it goes from my machine to a thing called restream.io, and then from there it goes out. Okay, so what I send out is exactly the same thing for YouTube, Twitch, and Microsoft Stream. Okay, anyway, sorry for that annoyance, but it seems like, as far as I can tell, it's a Twitch issue, not an issue at my end. All right, with commits, you can have a parent-child relationship. Okay, and you're going to see this in a lot more detail soon. And in I think it's this week's lab, you're going to do a Git exercise, or maybe it's next week's lab. I don't remember. In this week's lab, you're going to do, or next week's lab, you're going to do an exercise in your group where you do a whole lot of commits, and you make intentionally. You're following a script that I give you. You make mistakes deliberately, and then you fix those mistakes up, okay? Because this is what actually happens in real life. People make mistakes when they're using any sort of version control system. So we're going to walk you through some mistakes and then fixing those mistakes up. So when you do it in the lab, a lot of the concepts I'm going to talk through here become a lot more concrete and real. So if you're not following this, don't stress too much. Okay, so for every time you say commit, it will capture all the changes you made to some set of files. You can specify which files they are. Okay, you can say just this file, and that file, and it's a coherent set of changes. And the whole idea is you determine, as the user, what a coherent set of changes means. It may just mean that little change to that file, or it may mean this set of changes, because it may be the case that your changes need to be together to make any sense at all. Okay, changing this file doesn't make any sense unless you also change that file. That's why you're allowed to have a group of files in one commit. And it's very, very important that you, as a user, try to make sure your commits are coherent. So if this file does depend on that file and you've changed both, you should have them both in the commit. okay? And that is not a low-level technical issue. That's more a conceptual issue. More you thinking about, what am I doing here? What am I trying to change? And trying to make those commits be coherent changes to the system, okay? Now, there's a parent-child relationship among commits, and the parent-child relationship says, I was at this commit, I imported the thing from, I made a clone, I imported it from GitLab, and so the last commit there was probably the original import that I did, okay? That will be where you start. And then you'll do another commit, and that will be a child of the prior commit. That's what we call it, okay? So it's a parent-child relationship, but you can have multiple commits come from a single parent, which sounds a bit weird, but that's what we call a branch, okay? So you can go back to this one and make another child, okay? And that's what we call a branch. And why would you ever want to do that? Does anyone know why you ever want to do branching? Why do you want to develop two different ideas separately, okay? Normally you just want a single line of development. So I start with this, I refine it, get to this, I refine it, I get to this, I refine it, get to this. Sometimes you want to say, I start with this and I start refining over here, and I also start refining here in a different direction. Why would you want to do that? Yeah, testing is a great thing, and new features, okay? Both those are great suggestions for why you might want to do this, okay? So you're in a group and you say, hey, Bob, you go and do that thing and mess around with it, and we'll keep working on this thing. And when you've finish messing around with it, let us know, and then we'll bring your changes into our stuff, okay? And that allows Bob to keep using Git, and Bob's changes are still there, and you can still look at them if you want, but they're in a separate branch. They're in Bob's branch, okay? And Bob does all these changes and says, hey, I think it's all good now. And you can look at it and say, oh, great, let's merge it in. And then you can take Bob's changes and merge them in. And you're going to learn how to do that soon, okay? But you don't even need to have multiple people to make this useful. You can be working along really well, and you're developing things, and you're like, oh, I think maybe what I want to do is this. And then you do those changes in a branch because you're not really sure if it's going to work or not. And you work away there and you go, oh, that didn't work. And then you go back to where you started, okay? That's a very, very common practice. It's a very powerful tool. Now, one of the most, let me say something more about the social dimension of coding, or the psychological dimension of coding. And programming and working in teams is incredibly very much a human thing, a personal thing. And one concept that a lot of people underrate terribly, and I think a lot of people don't come to grips with very quickly, is that you need to be courageous. Okay, courage is actually incredibly important to programming. And if I use the analogy of the musical instrument, if you think back to the musical instrument, that analogy holds true there. You can't do interesting stuff in music, for example, unless you're courageous. Courageous in the sense that you're prepared to stand out on the stage and make mistakes in front of a whole lot of people. Okay, that takes courage. It takes a lot of courage, actually. Okay, but unless you do that, you won't extend yourself to the point where you can play really well. Okay, so that takes courage. And the same is true when you're coding. You've got to be prepared to make mistakes. People like me, when I code, I know do a lot of coding, I make mistakes all the time. Okay, and some of you might not realize that. You might be thinking, if I make a mistake, that's a terrible thing. Terrible thing to make a mistake. It's not at all. It's actually a normal process. That's how you learn. Okay, and why am I digressing on this whole thing about courage and making mistakes? Because A, you're not going to become a really good programmer unless you really embrace the idea of failure and making mistakes, because it's absolutely natural. And B, that's what version control is all about. It's about protecting you, okay? So being a tightrope walker and being up on that high wire, it takes a lot of courage, but it would take an extra lot of courage if there was no net beneath you. The version control is your safety net, okay? So if you really screw up, you can go back in time to a previous revision that was all good and everything worked, okay? And that's also why we have continuous integration and testing. So you know when you do this commit, oh, look, it passed all the tests, or it passed the test that I knew it was going to pass, okay? So I know this was a good revision. And that's exactly why we have continuous integration. So you can see that when I did this stuff, that was all good, okay? Then if things all go to heck, you can go, what did I do wrong? And you can look back and say, you know what, it was all working just back then. Let's go back there, throw away the stuff I just did now, and start again just there, because I know for sure it was working there. You need to be thinking like that when you code, okay? And this is not like cooking, right? If you cook, I cook a lot, right? When you cook, if you make a mistake when you're cooking, that's kind of annoying, because you can't unscramble an egg, as the saying goes, right? You can't often undo stuff. But with coding, you can. And with music, if you're not in a live performance, you can too, because you can just start the piece over again, okay? But With cooking, it's a different thing. So please don't think of, although I do use cooking analogies sometimes, please don't think of coding like cooking, because you can undo stuff here. Update will default take you to the head, which is the most recently known commit, but you can update to any particular revision. This means you can jump to a particular place, and you can do this in IntelliJ through, it shows you on the screen there. You can go to VCS, Git, Show History, and then you can select a revision. You can jump right to that revision, okay? And then if you start making changes at that point, you're creating a branch, okay? So the notion of a branch so let me just recap some key ideas here. A commit is a coherent set of changes to some number of files. A branch happens, and then commits have a parent-child relationship, okay? Which is when you develop your system. When you have two children from one parent, or more than one child from a parent, that is called branching, okay? So as soon as there's more than one child, that's a branch, okay? Or branches. You can have multiple branches if you want. And a merge, by contrast, is when you've got a commit which has got multiple parents, when you bring together two things and make a single thing again, okay? When you bring it back together, that's called a merge. And so these are very, very important concepts. Merging is when you bring things back together again. Branching is when you take things apart and develop things concurrently. I preempted the slide, evidently. A branch occurs when a commit has more than one child. A merge is a special commit with two parents that brings things together. It unites branches. Okay? If branches are conflicting, those conflicts need to be resolved. Then IntelliJ steps you through that. Okay? So if you have to try and merge conflicting results, IntelliJ will step you through that. And in your lab exercise, you actually have to do this. And I step you through it in fine detail. Okay? So you don't need to be intimidated by this idea. So what's going to happen in your lab exercise is you're going to go and develop stuff. You're going to do conflicting changes. We're going to make you do conflicting changes on purpose if you follow the script. And then you're going to have to merge them. And we show you how to merge them. Okay? Because in real life, this happens pretty often. Amend, reset and revert. You can amend a commit message with amend. That's kind of useful sometimes. If you make a commit and you realize you forgot something, you can add something into that commit after it's been committed, but not after it's been pushed. Once it's been pushed, it's been sent out to the big wide world, and you can't do anything further with it. You can reset your local state by using reset, so you can essentially throw away stuff, so stuff that you haven't sent out to the big wide world. The notion of push and pull are really important, because when you push something, it means you've told the whole world about this. If you've just done commits and haven't pushed them, then they're kind of private to you, and you can back off of stuff or undo stuff in a way that's not public. But once you publish them by saying push, then all your colleagues who are working on this thing, they'll see the change, and so you can't really wind back. The only thing you can do is use revert. And what revert does is revert takes a commit and then makes a new commit, which is the opposite. Okay? Now think about going to the bank. If you go to the bank and you type in you want to take out $10 or $100, if you want to take out $100, then and you actually mistype and you take out $1,000, then you can't just undo it like that. You can't just suddenly not take out $1,000. It's too late. The cash is in your hand, right? If you did that by mistake, right? And that's like your rent for the month, right? You've accidentally taken that out of the bank. You didn't mean to do that, right? So what do? Well, you can't undo it and magic it away. What you have to do instead is you have to put money back in, okay? That's a revert. It's very close to the revert. So the way banks work is in these strict ideas of transactions, very much like commits in Git, and you can't just disappear a commit. It's kind of there for good once it's been pushed, okay? But you can create a new commit which undoes the effect. So you can go and go back to your bank and put the $1,000 back in. So if you go and look at your transaction record, it'll say took out $1,000 and they'll say put back $1,000, okay? So it didn't make them disappear altogether, but it has a counter effect. It has a counteracting transaction, and a revert is like that, okay? Upstream pull and update are actually completely different. An update is more like a checkout. I think the stuff on the slide there is what we call checkout. You can check out a particular revision, but in IntelliJ you do it with a mouse click. Okay, an upstream pull is a different concept altogether. I'm looking at the chat here. There's no such word as update. I had it on the slide. I'm not sure how that crept in there, but you can update to a particular. So that's in inverted commas, and I guess. I'm not sure how that got on that slide. It's a good question. So Leo's right, and he's saying it doesn't actually exist as an actual word. I think what we mean there is checkout. Okay, so checkout is an actual real word in Git, and checkout says I want to check out this particular revision. But if you're using IntelliJ with its drop-down menus and so forth, you just go to a particular revision and say, get that one out. Okay, we call that a checkout in Git. Okay, that's different from an upstream pull. Upstream pull says, I want to grab some changes that were done somewhere else. Okay, and we covered that in the lab previously. All right. Now, I told you before that we use Git for a good reason. One of the problems with Git is it is complicated. Okay, it is complicated. I apologize for that, but I also point out to you that one of the things I try to do in this course is expose you to real-world tools. So hopefully I provide an environment in which you can learn this complicated thing kind of safely in a way that's minimally stressful. And IntelliJ does help you because it has nice drop-down menus and nice interactive tools that allow you to use it relatively easily. And we do teach you it in the labs, and we will be teaching you that in the labs. Okay? But really using it, the command line is monstrous, so hopefully no one's teaching you to do that. I think some courses do that. I think that's a really bad idea if you're a beginner to try and learn Git at the command line. It is a very powerful tool, but it is it's famously unpleasant, and this cartoon illustrates that point. Anyway, hopefully one of the things you'll get out of this at the end of the semester is this sense that you've learnt to use some very, very important tools that are used all over the world by people in industry and in academia and people everywhere. All right, now let's do our quiz for this. Here we go, publish the poll. And we'll move on to the next unit. All right. The next one is our next step on software development teams. And this is an incredibly important unit. It's a new one I wrote last year. And I do want you to pay attention to this. I actually don't have a mini quiz for it, I just discovered. I forgot to make a mini quiz for it. But this is examinable, and you can be guaranteed it's going to be an exam. But more importantly, you're going to need it during the semester to deal with your teammates, okay? And this is a quote from one of the titans of software engineering, Tom DeMarco. You need to look at this quote and understand it. Okay, there's kind of a joke where the sketch comedy joke where some drunk person's looking under the lamppost and for keys, and the person says, "Why are you looking here?" And they say, "Well, because the light's better here." The chances are that the keys are actually somewhere where the light isn't, okay? The point is you need to not think of technology as necessarily the reason for the problem. There's a bigger problem than that. Very often it's the sociology of the group you're in, and just referring all the time to technology issues is absolutely missing the point, and that's what they're saying here, okay? So, very interesting question. Why do software projects fail? You guys don't want your software project to fail this semester, but failure of software projects is an incredibly real thing. It happens again and again and again in industry and in government. And there are some terrible examples. If you do a quick web search, you'll find all kinds of examples of catastrophic failures of software projects. Okay, and these often run into millions, sometimes even into the billions of dollars due to software project failure. And there's a whole literature of stuff out there on why this happens and what causes software to fail. I'm going to refer here to a study, and there's a URL there, and the course webpage has a whole lot of references. Please go to the course webpage and look at all the stuff I've put on there for you. But I want to refer to the study here. Google cares a lot about how teams work. They have a very pointy, very tough hiring process. They try to hire really good people. And they care a lot about how people work in teams. So they've studied this a lot. They've tried to study what makes a team effective, what makes good outcomes in software happen, okay? And team effectiveness is a large part of this. And I think I mentioned earlier, I spent 3 months working at Google in this last summer, which was a lot of fun. And it was kind of cool to see this happening on the inside. But I'm going to refer here to this big study. And yeah, and so actually before I jump there, I gave you a bit of a preview. I want you to write in the chat now, what things do you think would affect the effectiveness of a software project outcome in terms of the team? Okay, so you've got a team of people here. It could be anywhere, all right? We've got a team of people here, and what things affect what things make teams more successful or less successful? Can people guess? Okay, and yeah, communication, great one. Great one. Yeah, team chemistry, that's a good one. All kinds of stuff. Please write down your suggestions. But what's interesting here is that what a lot of people say, and if your suggestions are wrong, don't be surprised, because actually most people don't get this right. And one of the things that was interesting about the Google study is that what people often thought was important actually wasn't important at all. And that's what's so revealing about it, okay? So let's have a look. They considered a whole lot of factors, including things like whether the teammates are co-located. You know, are they right next? Someone's passed on a reference to a $125 million software failure. Don't do that, please, folks. If you're a graduate of mine, I don't want you having $125 million failures. So whether the teammates are right next to each other, it doesn't matter if your teammate's sitting at the desk next to you or if they're sitting in another country, right? I do a lot of work with teams that is distributed around the world, and that makes things interesting and challenging. Doesn't matter whether you have consensus-driven decision-making, or that consensus means that people come to an agreement amongst themselves, or someone telling them what to do. Doesn't matter whether the team members are extroverted or introverted. Okay. Does it matter if the individual performance of the team, or does the individual performance of the team members matter? Is it really important to have a superstar on your team? Is that going to change? Is that going to change the outcome? What about the size of the work? If you give people really huge projects, is that somehow are they going to be worse than if you give them small projects? Will the outcome be better if you've got a lot of grey-haired folks on the team, or if you've got really young folks on the team? What's going to affect things? What about team size? Small size teams better, or big ones? And tenure means, is this person been around for a long time or guaranteed to be in the company for a long time? Have they got a job for life, as it were, or is it someone who's on a short-term contract? So if you can see any of these that you think are going to be major factors in the team, write them in the chat, because I'm interested to see what you all think here. And I think you really need to think. You all need to sit down and think for a moment about these factors, because you need to actually be a little bit introspective and think about what you think is going to make your team effective. Okay, remember, you don't even know who's on your team yet. Okay. All right. So here's the punchline. Okay. What they found was none of those things significantly impacted the performance in this study. Okay, it doesn't mean they're not important, but what they meant was none of them made significant impact on the performance. Okay, so that's really interesting, and that's surprising. Okay, if you're surprised by that, don't be worried. That's a really interesting outcome. What they found was the number one thing is what they called psychological safety. Okay, team members feel safe to take risks and be vulnerable in front of each other. Now, I don't know if you noticed, but I'm making mistakes in front of all 400 of you all the time. Okay, and I feel comfortable doing that because you guys are all really nice and no one's been yelling at me yet, not too much anyway. Okay, that's a question of psychological safety and self-confidence. Okay, I'm obviously confident because I've done this before, but I need to feel like it's okay for me to make a mistake, and I think I've made mistakes already today, right, in the coding. Okay, I made mistakes with the tech. I didn't have my mic working right. Okay, you got to feel like it's okay to make mistakes. If you can't do that, you become paralyzed. And the interesting thing in this study is, and now remember, Google makes a huge amount of software, and they spend an enormous amount of money on salaries. Okay, Google pays their employees really well. Okay, very well. So they have a huge financial investment in good software engineering. And what they found is number one was psychological safety. Okay, and that means you feel okay taking risks and making mistakes in front of your teammates. Okay, so if you don't have that, that's what you need to address. Okay, then the other issues they found was team members get things done on time if they're dependable. So these are people who are dependable people. Having dependable people in your team is really important. Structure and clarity, knowing who's doing what, rather than saying, oh, that person's a superstar or this person's an old person with tons of experience, or those sort of things, right, which you might have thought was important perhaps. What they say is what's really important is people know what's going on. We know we're going to do this. We know that person's going to do that part and this person's going to do that part. Okay, meaning's also really important. Okay, meaning in the sense that I actually really want to make this thing work because I think this is really interesting. It's an interesting problem, and I really want a really good outcome. I want to change the world by doing this. I want to build this great tool or whatever, and it means something to me to make a good thing here. I'm not just doing this because my parents are telling me to. Okay, if that's your motivation, then you're screwed. Okay, you need to be in here because you think you're going to learn something because you're actually interested in it. And finally, team members think their work matters and creates change. And this is something you really notice if you work at a software company like Google. I mean, it's very cool for me. I was working on the garbage collector for Chrome. So stuff I did went into the Chrome browser engine, which is used by 1 billion people. That gives you a really great sense of impact, and you won't do that with your COMP1110 assignments, but that might be the sort of thing you're doing soon. In fact, I got an email just yesterday from one of my former students saying they just got a senior position at Google in Sydney, and that made me super happy. And I'm going to see if I can get her to talk to the class. She may not be able to, but if I can, I'll see if I can get to her to talk to you all. Okay, she's one of my former PhD students. And the point there being that having an impact like that, where you can change software that affects a lot of people, is very cool. All right, conflict resolution strategies. Conflict is part of any work environment. There will be conflict. I have a collaborator I've worked with since 2000. Year 2000, okay, so we've worked together for a long time, and we have arguments all the time. We often argue, but the thing is, we know how to argue well, and we get a lot done, and we've done some great work together. We've published 30 or 40 papers together, and done stuff that's had huge impact all around the world, and I'm very proud of that stuff. And that has come through a work context with a collaborator who I trust, and who I've got to know with, and with whom I know how to have conflict successfully, okay? We argue a lot, as I say, but we know how to resolve those arguments and work through them. We don't take it personally, okay? And we work under stress a huge amount. She's at Google in the US. She used to be an academic at University of Texas. But we do a lot of stuff that's very, very high stress, and we know how to deal with each other under very, very stressful situations. So that is part of being successful, is knowing that people are imperfect and knowing how to deal with conflict when conflict arises, because you will have differences of opinion. It's going to happen, right? It's a question of knowing how to deal with it well. So here's a list of 10 key conflict resolution strategies. You see the citation down the bottom there from someone called Stephanie Ray. So you need to have an agreed frame of reference. You need to know what's acceptable behavior. You don't avoid conflict. This is incredibly important, okay? Incredibly important. Don't avoid conflict, okay? If something's going on, some of you think, oh, I need to step around the conflict, okay? And it's culturally, many of us learn to avoid conflict. Culturally, many of us say, no, you don't want to have conflict, okay? But this advice here, by people who study this professionally, is you need to expose yourself to that conflict and deal with it properly, okay? You don't step around it. You say, hey, there's something we're not agreeing with here. Let's talk about it, okay? Rather than just pretend it doesn't happen. And when you do this, you do it in a neutral location, which is kind of happening by default here when you're virtual. But when you're doing it in a physical environment, having them come to your office, for example, is a biased situation. If you go to a coffee shop or something like that where you're both neutral, then that's better. Start with a compliment. Say, hey, I really like the way we're working together on this. I really like what we're doing here. Before you say, and by the way, what you did there really sucked. Okay, start with a compliment before you say something negative. Don't jump to conclusions. Don't think, aha, they've written that piece of code there because they hate me. That's probably not the reason why they did it, okay? They probably wrote that piece of code there because they weren't thinking, or they were concentrating on something else, or they were really stressed, something happened to their pet dog, or whatever it might be. I mean, quite literally. All this sort of externalities may have been the reason why something happened. So don't jump to conclusions and imagine the reason why they're doing it, and don't imagine it's all about you. It may have nothing to do with you. Think opportunistically. Hey, look, we've got two different ideas here. Maybe we can come up with something even better because we're thinking differently. That's great. And rather than punitively, hey, you know, we can't do your idea. We're going to do my idea. Offer guidance, not solutions. Okay, someone's doing something different. Instead of saying, hey, you need to do it this way, say, hey, you know, I found it really useful to look at this tool over here, or I found it really useful to read this book over there. Constructive criticism. Don't just say, oh, well, that just sucks. I don't like it. Okay, that's not helpful. Okay, you say, you know, if you did it this way, then both your thing and my thing would work really well together. And don't intimidate, okay? So try not to get into their face and poke them in the chest. And act decisively. Above all, act decisively. So don't let things fester, okay? That's like number 2. Don't avoid the thing. And please act decisively. Code of conduct. There's a code of conduct on our webpage. Please look at it, okay? Please look at it. People seem to misunderstand the word argument. Yeah, you know, I used to work at Intel, and at Intel they had this slogan, disagree and commit. There's a very strong culture of argument, okay, and it's all about thrashing ideas out. In academia, this is absolutely the case. You go nowhere in academia unless you're prepared to tussle with ideas and wrestle with ideas, okay? But basically, academia is like one huge intellectual wrestling match, okay? You've got to throw ideas around, and you've got to be prepared to argue your case, but not take it personally, okay? And you've got to be able to manage conflict though, okay? So we can't do conflict in a way that hurts other people. That's the important thing. You see right in the middle of the screen right here, above all, be kind. You've got to be kind to other folks, okay? So if the way you're dealing with an argument or the way you're dealing with conflict is not being kind to other people, you're doing it wrong, okay? So that's very, very important, okay? All right, there is no mini quiz. Sorry about that. I didn't actually make one. My bad. All right, next. What's the time? Let's just take a very quick break now, and I'll get a coffee, and we'll be back in about 2 minutes. All right? I'll try and make my coffee fast. All right. Okay, mic should be back on now. And let's get into the next unit, which is about the number types and autoboxing. So there are a family of classes in Java called number, and the key idea here is that you so far you've learned how to represent different numbers in Java using what we call the primitive types, which are int, float, etc. But Java also has what are called boxed types, which are objects which are analogous to these primitive types. Okay, now let me explain this a little bit more. Now, you all know what a box is, right? You all know what a box is. Actually, I just got a box just arrived right now from Amazon for me, right? So it's a box, right? Brown. I could have brought it upstairs. It's a brown cardboard box, right? You're familiar with that concept. What are the advantages of boxes, physical boxes? Why do we have that? I bought some gadget and it's come in a box. I've got boxes all around me, right? Why does stuff come in boxes? Here's a box right here, from a gadget. All right. So why does stuff come? That's a piece of camera gadget, and it comes in I buy it and it comes in a box, and inside the box is the gadget, right? Why do we use those? There's a lot of reasons why we use boxes in the real world. Okay. We use them because they protect the thing inside. They make it easy to transport and so forth, right? That's why we use boxes in the real world, okay? But if I said to you, I want to buy some nails, right? You know, nails for my hardware, and every nail was in a box, you'd say, that's ridiculous, right? Why is that ridiculous? Because there's a cost associated with boxing things up in the real world, right? And if every separate nail was in a box, that would be very wasteful, right? Instead, we have a box full of nails, right? Okay, now in Java, objects actually have a small cost associated with them, just like boxes do. And we actually use the language, not just in Java, but in other object-oriented languages, of what we call boxing, where we create an object which contains stuff, okay? And we can have objects which contain just simple numbers, like an integer, a short, or a float, and so forth, okay? But we pay for the cost of the box. Later on in this lesson, we're going to look at it, this in the Waterloo Visualizer, which should make it much clearer to you. But I want to point out that we have this relationship in Java with these primitive types, which aren't boxed. That's like your nail. And these boxed analogs, which is integer, short. Notice the capital I, the capital S, and the capital F. Those things are actual objects, okay? So int, short, and float are not objects. They're what we call primitives. Primitive types, okay? And they don't exist as objects on the heap. So when you look at them in the Java Waterloo Java Visualizer, you don't see something on the heap. Instead, you just see the little thing on the stack, okay? Now, why do we want these? Well, we're going to get to that soon. But these are useful sometimes. They come with the power of encapsulation, as someone pointed out, and they actually have methods associated with them. And you can use methods on integer, methods on short, and methods on float to do things, okay? Whereas a normal short, float, and int don't have any methods, okay? You can just use operators like the plus operator with 2 ints, or the greater than operator with 2 ints, and so forth, okay? But these classes, these are actual classes, and they actually have operators that you can use on them, which we're going to see in a few minutes, like toString, parseInt, and so forth. Primitives don't have methods because they're not objects. Objects can have methods associated with them through the classes that they are members of. Okay, and the number classes also have constants like integer.minValue, which is the minimum value that an integer can represent, and short.maxValue, which is the maximum value that a short can represent, and so forth. But as my analogy with the cardboard boxes should have illustrated to you, they come with a space overhead. Okay, so there's an overhead associated with putting things in a box. That's why with things that we use really frequently that are really important to computation, we actually unbox them. We don't put them in boxes. And so far in this class, you've been doing ints and so forth, not in boxes, but as primitives. All right. Autoboxing is this concept in Java where it figures this out and it knows in the language that the relationship between a boxed int and an unboxed int, and it magically, automatically moves things between the two. So here in the first line there you see automatic boxing. So the literal on the right there is the number 5, which is obviously an int, and the value on the left there is I, which is a type integer. And so what Java does is says, oh, we've got an int on the right and they've got an integer on the left. I know what I can do. I can turn that 5, put it in a box and give it to I. So now I is a boxed value of 5. And conversely, we can take I, which is an integer type, and assign it to j, and it says, oh, but the thing on the left is not an object, it's a primitive, int, whereas the thing on the right is an object, but they both happen to be of the same underlying type. That is, the thing on the right is actually an integer. So I can pull the value out of the box and give it to j. So now we get the value inside of I and give it to j. And that happens automatically in Java. It's one of those things that's automatic, which may be confusing when things happen automatically, like a sleight of hand. That can confuse you. So I'm telling it to you explicitly, and we're going to do some examples in a few minutes in our code. Another thing which is separate, but not unrelated, is a thing called the math class, which is useful for a few things. And you've already seen me use it once. I used it for the max value, where we talked about redeemables. Okay, when I did that in the code where I did with redeemables, I used a thing called max to say the maximum of your exam mark and the mark you got for that thing. We used max, and that's an example of something that is offered by the math class. So what is what useful for, Katrina? You asked me about boxes. The usefulness of boxes in the programming language is a bit like the usefulness of boxes in the real world. You can put stuff together, so I can have a special thing which has an int, a float, and string all in one object. So my object contains those three things. The int and the float are both primitive types, but I've put them into a box, okay? But do I very often have an int just sitting in a box? Not very often. It's not very often useful. But more generally, creating objects out of these small parts is useful. Just like having things in boxes in the real world is useful. And just like creating a box for every single nail is generally not useful. It could be, but generally not. Okay? So it depends on on what you're trying to do with them. Okay, so every object is a box, if you want to think of it that way. That's what boxing means, putting it in an object. And usually we don't put primitive types into boxes, but there are certain circumstances where we have to. And we're going to come to that in a few minutes. We're going to come on in a few minutes. Later in today's class, we're going to come to a place where Java requires you to use boxes, okay, for interesting and complicated reasons. And in that case, you'll have to use the box, all right? But generally, it's simpler not to use the box, all right? There's a whole bunch of features you can get from the math class. That they're right there. Okay, we're done with that. Let's get on with the mini quiz. Here we are. Open the poll up. There it is. And we can move on and do our boxing. This is kind of fun and fairly fast, I hope. So we're up to unit J10, and we're going to create a class here called a boxing. J10.boxing, and I need you all to answer some questions as I go along here to help to see if you can see what's going to happen. This is a little bit tricky, and this is going to be really useful to look in the Waterloo visualizer later. We'll do that very quickly at the end of this, okay? Because some of this is kind of a little bit unobvious. PSVM, whoops. Okay, create ourselves a main method. Now what we're going to do is we're going to create a boxed integer, a. So a is going to have a box, and it's going to have a little int sitting inside that box. And we're going to use the new method to create that integer, and it'll be 6. Okay, so the value of the integer will be 6. So a will be a box that has the number 6 inside of it. Okay. Now, and why has it got that line through it? I forget why. You don't. Yeah. Because IntelliJ is telling me to do something which I'm about to explain to you. Okay, so it's jumping the gun. In fact, the very next line of my example does exactly what it's telling me to do. What you can do instead is this, like that, and those two lines are actually equivalent. Okay, because what's going on here is that is not a boxed integer, right? That is actually just a literal int. And what Java does is, oh, you're trying to make an int and assign it to an integer, and it says, you know what I'll do? I will turn that int there into a boxed int for you, and that's what B will refer to. So B will refer to the boxed int 6. Okay, so this is auto boxing, and this, if you want, is explicitly boxing. Right? And IntelliJ says, hey, you don't really want to do this. That's why it's put a line through it. It says it's unnecessary. You don't need to do that. Okay, but I'm doing that to show you the concept. Okay, so what we have now is two boxes: box A, which has the value 6 in it, and box B, which has the value 6 in it. All right, think about that for a second. All right, try and visualize that in your head, because I'm going to ask you a slightly twisty question in a moment. And the other thing you can do is you can do this: you can declare an int C and say that is equal to A. And that is auto unboxing. So on this side, you've got an int. On that side, you've got an integer. And what's happening is Java saying, that's fine. It'll take the value from A and give that to C. So it'll take the int that is inside of A and give it to C. So this is auto unboxing. All right. Now comes the interesting part. I'm going to get you to quickly tell me on the chat what you think is going to happen here. All right. I'm going to make this pretty. I'm going to print something out. If A equals B, this will get printed out, okay? And in a minute, what I want you to tell me, is this going to be true or false? All right, someone says false, but that's not obvious. All right, so I want you to think about this. Is that going to be true or false? Is this here going to be true or false? You can see everything on the screen. There's no magic here. Well, there is actually a little bit of magic, but see if you can see what's going to happen here. Actually, I'll just copy that whole line. Someone reckons it's false, but it could be true. Let's see what we think. Error, true. Right, true. Some people say true, some people say false, okay? So what we're going to do is we're going to test this here. Which line will get printed out? This line here, which says that they're equal, or this line here that says they're not equal. And I really want everyone to commit here. This is where you got to be brave. I told you got to have courage. you got to have courage to learn, folks. So you got to put a stake in this. You can do it privately if you really don't want to put it on the chat, but I want you all to decide, is this going to evaluate the true or is this going to evaluate the false? There's A and there's B. Look, they're both boxes with 6 in them. Okay, and so let's run this thing and find out the answer. Okay, let's run it. And the answer is they're not. Okay? Now, this might be really disturbing to some of you, which is good, because that means you're thinking. Okay? Okay? But in a minute, we're going to look at this in the Waterloo Visualizer, and it'll become very good. Okay, so Tian Yi said it exactly right. False, because they refer to different things. That's exactly right. There's 2 boxes that both happen to have 6 in them, but they're different boxes. And what that question there is actually asking is essentially, if we want to make it verbose, it's saying, is box A the same thing as box B? And you're like, no, they're not the same thing. They have the same thing inside them, but they're not the same thing. Okay? And that's a very important and really subtle difference, and it trips people up a lot. So what you really should do is go and look at the Waterloo Visualizer, and it becomes absolutely clear that A and B are both boxes, and there's different boxes that happen to have the same thing inside of them. Okay? But they're not the same box. And that double equal sign there is saying, is this the same thing as that thing there? Now, there's something else we can do here. There is a way. Does anyone know how we can find out? Yeah, good response, Katrina. This is mysterious, right? So if you're confused by this, don't be. You're good, right? That's fine. There's something else we can do in Java, which is this. Okay, the equals operator. Okay, and these 2 things are different, and this is really, really important to understand. Okay. And what equals is going to do is it's going to say, are these not equals? Now, let's run this, right? And we get the answer you expect. And what this is doing is this method here called equals allows Java to look inside of A and say, is the thing inside of this the same as the thing inside of that, making these 2 things equivalent? And the answer is, of course it is. They've both got 6 inside of them. So yes, they are equal in that sense of the word, with the equal spelled out in English. Whereas this here is saying, is A the same thing as B? And it's like, no, they're not the same thing. They're both boxes and they both have 6 in them, but they're not the same box, okay? You need to get this idea clear in your head. Watching the Waterloo Visualizer should make it really clear. So please take the time to get this clear. And if you're puzzled by it, like some of you are, that's absolutely fine, because this is a puzzling thing. All right, then the last thing we're going to do is do this again. Someone says, why doesn't Java do its magic? Well, it does under certain circumstances, and you need to understand where. All right, and if we do this, we get a different outcome. So see if you can guess what's going to happen here. Is this going to be equal or not? Right? Look up here. You can see A, B, and C all up there. And now we're going to ask if they're the same. Okay? Let me just change this. Let me change this to B to make it a bit more interesting. There we go. So, is that going to be equal or not? Okay? And the answer is, let's run it. Okay? They are. And what's going on here is interesting. What Java says is you've got an integer, boxed integer here, and you've got an int here. And it says, well, you can't compare them because they're not exactly the same. But you know what? I know how to turn an integer into an int. So I'm going to turn them into the same thing. So they're both ints now. And guess what? They both turn into 6, and 6 equals 6. So of course they're equal. Okay? So that is auto unboxing there. Okay? And I'll take a sip of my coffee. All right, and that's. Oh no, let's very quickly look at this with the visualizer. So we go here. We're in unit J10, I think, and we go here to the J10. Where are we? Boxing and unboxing, and we're going to very quickly step through this. Run it forward. Okay, so there's A. It's a box with a 6 inside of it, okay? There's B, a box with a 6 inside of it, okay? And there's, here I've called it Z. So Z is equal to A, and that means A and Z are both referring to the same box, okay? And then I've said C is equal to A. C is actually an int. So my example here isn't exactly the same as what I did in the lecture, but it's pretty similar. So I've created a new thing, which is C is equal, and I've got two things here, which are both ints. Y and C are both ints, and they both have the value 6. So now what you've got is two boxes over here. One box here, one box here. This box here is A, that's A. That one there is B. But this one here is also referred to by Z. So this is A and Z both referring to that box, and B referring to that box. Now, if I go and ask, is A equal to B, it's saying, is this thing the same as this? And then the answer is no. They're both references, and they refer to different boxes. Okay? And that's why you get that. And if you say, is A equal to B, it'll look inside of A and B and notice that they're both 6, and so it'll say sure. Now, if you say, does A equal C, it'll say, oh, what's inside of here? That's 6, and C is an int 6, and it'll compare that 6 with this 6 and say, yes, they're equal. Okay? All right. Let's get on with the next section. It's espresso, Brendan. It only needs to be a little cup. All right. Next section is J11. And J11 is very, very similar. Okay, we just did ints as boxes. We're going to do characters as boxes too. Okay, so you got char, which is the unboxed character. You use that in your assignment, and I've already told you about this. Character is to char what integer is to int. Okay. And then you've got the character class. It boxes char, just like integer boxes int. It contains methods and constants useful for manipulating characters. So you can do things like is letter, is digit, which is kind of useful. You can take a character and say, is that thing a letter, is that thing a digit? And it can do things like conversion. It can convert a character to a string. Okay. All right, we've got the string class. You've seen a lot of this already. Okay, you can create it from a string literal like that, which creates a string object with FOO inside of it, and you can do concatenation, which creates a new object Y, which has got that plus this. Okay, and you've got a thing called the string builder class, which we're not going to spend a lot of time on in this course. You can get the length of a string using this special method here. That's part of string. You can get a character in a string. You've already seen this multiple times. I've showed you this multiple times. You can get a substring. You can split a string into parts, and you can trim a string. You can turn a string into lowercase, uppercase, all kinds of stuff. You can go and look at the string class online and find out all these different things you can do with strings. You can find something within a string. Index of will find the first occurrence of something. You can find out whether it contains something, which will return a boolean saying, yes, this does contain this substring. And you can replace things. So replace all occurrences of the letter H with a lowercase h or something like that. All right, that was quick. So J11, publish the poll, and let's go and write some code. Hopefully this will be fairly quick, and we might even get on to the last part of the lecture today, which would be awesome. New Java class, and the class is going to be what's happening here? Which one are we up to? J11. All right. Yes. Okay. Cool. All good. I got confused here. This is fun. All right. This is a fun one. I like this. Boggle. All right, we're going to do more on Boggle later in this semester because we're going to actually do a game. But I'll quickly tell you what Boggle is. If you go here to your favorite search engine or any search engine, there it is. Oh, it's already down there. Okay, and we type Boggle. It's actually a silly game, very simple little game. There it is. There, it's a word game. Okay, so this thing comes with a plastic cover on it. Let's go to here, the Wikipedia one. It shows it to you very clearly. There you go. So you got 16. Dice here, 16 dice. Each one has obviously 6 sides. Each one has a letter on it, and you got a plastic cover that goes over the top of this. You shake it all up and you make them all settle down. Then you turn this over, and then you play a game of trying to guess words that are in here. So you see GET is get, okay, NET is net, WET is wet, and so forth. Okay. And we've got someone in the class who's good at Boggle. Great, because you know what, Katrina? We're going to write a solver for Boggle later in this class. And so we're going to write a thing which can solve Boggle and give you exactly every single answer to Boggle. So you might enjoy that, but that's not today. That'll be later. Okay. But what we're going to do now is we're going to write a Boggle maker that will create the problems rather than the solutions. And later on, we're going to do the solutions. Oh, and I've done a little cheat here because what I've done somewhere here we go. As my little cheat is I just did this before the lecture to save me typing all this junk in. Oops, keyboard issues. That there is the 16 dice of Boggle with the actual 6 sides on each dice that are actually in the legal Boggle game. So not surprisingly, those letters aren't evenly distributed, so there's not as many Z's and Q's as there are other letters and so forth and so on. Anyway, so all I've done here is I've created 16 strings. There are 16 strings there. They represent the 6 dice that make up that thing. And each of these 16 has 6 letters in it. You can see each one of those is a string of 6. And so this allows us to create the game. And now what I want you to think about is how do we write a little piece of code which will basically randomize this. Now there are 2 steps to it. Think of it this way. Think of it as having a bag with the dice in it and then a grid, a 4x4 grid. And you're going to put your hand into the bag and pull out a dice and plonk it down there, roll it, and whichever face up it goes. So there's 2 levels of randomization. One is which dice you get, or which die you pull out, okay? That's one level of randomization. And the next one is which way it lands up, okay? So there's 2 levels of randomization, okay? So first of all, the ordering of the, so you pull them out and you put them in that grid, but you do it randomly by pulling them out of a black bag. And also when they land on the table, they land with a particular face up. So we've got 2 levels of randomization. And we want to write some code that does that, okay? So let's go and write that code. So here, what we're going to do is we're going to say, write ourselves a little program, PSVM, like that. And we're going to create ourselves. So what class do we want to use if we want to do random stuff? Okay, or rolling dice, okay? Random dice, okay? We use this. We use random. Hopefully you all know that, okay? Equals new random. So we create ourselves a random number generator, a pseudo-random number generator. You all know they're not really random, they're just pseudo-random. And then we need to know the length of a row. It's a grid, right? It's a 4x4 grid, so but we'll do that. Int row length equals the square. I'm going to do some gratuitous math here. I could have just typed in 4, but instead of doing that, I'm going to say math.square root of the length of the array. There you go. So that was kind of unnecessary. I could have just written in 4, but what that's going to do is take this array. It's got 16 entries in it. Take the square root of it, and now we've got row length equal 4. Okay. All right, now what we're going to do is we need to do this random pulling them out. That's one part of it. And then once we pull them out, we want to roll them. Okay, so one way to do this, one way to think this through is say, let's imagine we've got this array of dice, pull one out at random. So one of the 16, once we pull it out, we'll null it. We'll change it to null so we won't pull it out twice. What we don't want to do is to pull the same dice out multiple times. So you really do want to remove it, right? You want to remove it from the bag, okay? So you don't want to put it back in the bag after you want to pull it out and put it back in. That would be bad, right? What you want to do is you want to randomly pull one out and take it out of the bag so it's no longer in the bag. So what we'll do is when we find one, we'll null it from that array. And that way, when we go in, put our hand in again, we won't pick up the same one twice. All right? So let's do that. So what we're going to do here is for int I equals 0, I is less than dice.length. Because we're going to do this 16 times, right? We've got to make this grid of 16, and there's 16 elements in that array. And then we say I++. We're going to have ourselves a little for loop here. And then what we're going to do is going to say which die we're going to have. We're going to have one of those 16. So int die, which die will it be? We'll use rand, rand dot next int, and then we put in here dice.length, right? So what that's going to do, if you remember how rand works, is it'll give us a pseudo-random integer, which is between 0 and 15, which is the length of dice, -1, okay? So that's how it works. So that will give us an index into the array dice. And then what we can do is we can say, while it's not one we've already done, we're going to null them out, right? So, oops. So it could be that when we pull one out, it's actually nothing there because we've already taken that one, in which case we'll just fish again, right? We'll go fish for another one, okay? So then we'll say die equals we'll just move to the next one. If the one we've chose was gone, then we'll just move to the next one in the sequence. All right. So we can just do this. We can say die equals die plus 1. And what's the problem with that? If I do that, we've got a loop here. Okay, and we're adding on to die. That won't work. Why won't that work? Because when if we get to the end here, we go to 15, then we'll go to 16. Well, let's just run this. Why have we got an issue here? I'm missing a closing bracket or something. There we go. All right. So let's just run this thing here, and you should find with some chance, there's some chance here, not guaranteed to happen, is we'll get an array out of bounds exception. Exactly. Because what happened here is we added on 1 to 15 at some point, and then we got to 16. We don't want that. Okay. So it's so someone says we want to use modulo. We don't have a modulo operator in Java. We've got integer remainder, which is like modulo, but actually slightly more useful in this context. And then we say die.length, dice.length, right? There we go. So that's going to take integer remainder, and now we're good. So that's going to pluck out random dice. Okay. Now once we've found one, we want to roll it. Okay. So that's given us the dice, the die. Now we've got to roll that die. Okay. So now we'll say int face equals. How do we find the face? Again, we'll use the random thing. Rand dot next int, and there's six sides, right? That. Okay. And so we've taken the 6 sides. We've got a particular face. It'll be 0 through 5. And then what we're going to do is pluck out a character out of that string. So we've got a string here. We've got to pluck whichever one out according to which face it was. So we'll say the following. Say char value equals dice die dot char app face. Okay, and that will pluck out the character at 0, 1, 2, whatever that random number generator came up with. And now we've got to null out that die so we don't actually pull that one twice. Die bracket dice dot die actually this is a mistake. That should be with equals to null, not equals to null. Dice.die equals null. We're going to null it out. All right, and then what we're going to do is print out the value. All right, and that probably won't be pretty, but let's see what happens, and we can make it pretty in a second. All right, there we go. That's our 16 random letters, but let's make them slightly prettier. Get rid of the print len. Instead of doing print len, we'll just do print, which will make them all go in one line. You see that. And now what we want to do is we want to print out a new line every 4th one, right? So let's do that, and we'll just say if I integer remainder row length equals what? Row length minus 1. Then we do a print line like that. Okay, and run that again, and now we should get our beautiful little 4x4 grid. There we are. Okay, and each time we run it, we'll get a different. So now Katrina and other Boggle fans can play Boggle at the press of a mouse, press of a button. All right, there you go. We're playing Boggle. Okay, great. And later on, we're going to come back and solve this. Okay, that'll be in another lecture. All right. Now, wow, we've actually nearly got back on time, which is phenomenal. Cool. Let's go back to integer remainder does work on negative numbers, and it gives you a negative number, right? No, it gives you. It gives you a positive number. It gives you the opposite to modulus, right? So modulus, yes, sorry, it gives you a negative number, right? Linda, you're asking the question about integer remainder. So if you take integer remainder, you'll get a negative number if you do integer remainder, and you'll get a positive number if you do modulus, okay? I think that's right. You can go and test it. This is the sort of stuff that I'll get wrong, and the way I'll find out is by writing a tiny little bit of code and testing it out. All right, there's Boggle. That's not what I wanted. We wanted PowerPoint. Where are we? There's PowerPoint. All right, finally, we're on to generics. Generics is a very cool subject. Oh, yeah. So does anyone know what this is? Probably none of you do. Probably none of you know what this is. This is something from when I was a kid, okay? And probably... this goes back a long time, and this is a picture book. Richard Scarry, it was the guy who wrote these books, and it was full of pigs and worms and stuff like this, and cats and whatever. What's the reference here? The reference is he always drew pictures like this, And you'll notice that there's a truck here for pickles. That's the cool thing about this picture, and a little truck here for apples. And what he's done is he's made a special truck for pickles and a special truck for apples, which is kind of cute and fun, right? Notice that in real life we don't do this. Okay. Oh, someone knows about Lowly the Worm. All right, I'm so happy. Okay, that's Lowly the Worm, folks. That little worm guy, his name's Lowly the Worm. All right. Real life doesn't work like this. We don't really have pickle trucks. Okay, we don't have pickle trucks. Why not? We have generic trucks. We have trucks that do multiple things. Okay, and in fact, if you go look at a container ship, if you do a web search for a container ship, you'll find that container ships have modularized containers which are the same whether or not they're shipping a piece of electronics or some apples, okay, or some pickles. They'll have the same containers, all right? This is extremely useful, okay? We don't really want a special kind of truck that can only take pickles and another kind of truck that can only take apples. That's really not useful. So what we do is we make some sacrifices and make things not quite so optimal, maybe not so quite so cute as in these pictures, and instead we make a generic truck which can take a container box on the back and can take anything, okay? And that's how the real world works. And you'll see that on the highways. You go and look, you don't see pickle trucks, you see regular trucks, okay? Hopefully, and that's generics for you. No more generics. No, I will actually show you a little bit more than that. We'll get a little bit formal here. So sometimes it's useful to parameterize a class with the type T. So that means we're going to make a general container and say this particular one will hold ints and that particular one will hold characters, or this one will hold floats, or whatever it is, okay? And so rather than making a special class which only holds ints or a special class that only holds long, we can write a container which can hold type T, where we can specify T when we use it, okay? So when we design it and write the code, we just say it's going to have type T in it. We don't know what the type is, okay? When we use it, we say, we're going to put integers in this one, like we're going to put pickles in this one. We're going to put apples in this one, okay? We're going to put integers or floats or whatever in each one, okay? And we can also write generic methods that accept generic type parameters. So we can say, you can have some method that takes a value where the value is of type T. We don't know what it is yet when we wrote the code, but we've written the code very carefully in such a way that it can take different types of T. So it can take apples or pickles or nails or whatever it is, or cameras. Okay, so before we had Java generics, we got Java got generics, what we had to do is to do this sort of stuff is we used a thing called object. Turns out someone asked on Piazza about why we didn't use C#. Turns out that C# deals with generics a lot better than Java. And do you know why? You guys all need to know this. This could be an exam question. Why is it better? The answer here is right here, my friends. This article here, design and implementation of generics for .NET and Common Language Runtime. And who's Don Syme? Don Syme is an ANU grad, okay? I knew Don. I still know him, right? Don did his undergrad at ANU, got University Medal, I believe. If you go inside the building, you'll find his name on the University Medal list. Don did that. He then did his PhD at Cambridge. Then he went to Microsoft Cambridge. And some of you who follow programming languages may have heard of a language called F#. F# was built by Don, okay? And Don is the father of F#, the F# programming language. Anyway, Don's an ANU grad, and Don was, along with Andrew Kennedy, was responsible for generics in .NET, which don't suck, whereas the Java ones kind of do. All right, we'll see why later, all right? Wow, is that all I was going to say? I guess it is. We're going to write some code now, okay? That's it. So if you can't do, if you didn't have generics, you'd use object, because object kind of is, by definition, the most generic thing you can have in Java. It's like the word thing. Okay, so it's a truck for things rather than a truck for apples or a truck for pickles. It's a truck for things, which is what Java lang object is. Okay, so it's the idea that you completely get rid of any notion of type altogether and just say it's a thing. All right, which is not so useful. Why not use F#? Yeah, F# had the same issues as C# in the sense that it was quite proprietary and limited and so forth. That's all changed in the last decade. But F# is a functional language, which might make it a good candidate for COMP1110. Okay, and you know, if Don were here, he'd probably tell us we should be I'm sure he'd be telling us we should be using it. F# is a cousin of ML. I've got to digress here. I know we're running short on time, but I've got to digress here. Okay, so there was an academic in our department called Malcolm Newey. Malcolm Newey, a wonderful guy. He's still in Canberra. He's retired now, and he was around when I was a PhD student. And Malcolm did his postdoc with a very famous person called McCarthy. Okay, McCarthy. And McCarthy is one of the greatest computer scientists of all time. We haven't done his bio yet, but we will. McCarthy was responsible for a ton of things, including a lot of work in AI. John McCarthy. And when Malcolm was a postdoc with McCarthy, in the lab was another young guy, and he was the two of them became fathers of ML. And the other guy, I've suddenly got a name blank. Oh man, I can't believe I've suddenly forgotten his name. I'll get back to it in a second. But he's a Turing Award winner who I've actually met because he used to come to ANU, and they both taught ML, which is the foundational language for a foundational functional language, ML. And Malcolm taught ML, and he taught Don, and Don did his honors project with Malcolm. And then F# as a programming language actually borrows a lot from ML and from OCaml, which is another ML language. All right, and Robin Milner is the name that suddenly escaped me. I can't believe I forgot Robin's name. Robin Milner, and then we've got a room outside my office in the CSIT building called the Milner Room, and that's in memory of Robin Milner. All right, okay, let's get on and do this quiz, and we're nearly done for the day, and we're actually making okay time, I think. So, all right, what we're going to do now is write some code, and the code we're going to write is, first of all, we're going to write something very, very simple that I don't think we've done in our class yet, but it doesn't have terribly much to do with generics yet, but it'll illustrate the idea of generics, okay? We're going to make ourselves a linked list. A linked list is a very basic data structure, but we're going to make a very special one called an int linked list. This is like a pickle linked list. It's very specially handcrafted just for ints. Then we're going to make a generic version of this, which will work for different types, okay? So we're going to start off by making an int linked list, okay? And a linked list is a list that's linked, surprisingly enough. And it's a structure for holding values, okay? So what you can do is you can create a node that has a value in it, and it refers to another one which has a value in it, it refers to another one that has a value in it, okay? And so it's a list of things, and what they have is just, each one has just two things in the node. One is the actual value, which is an int in this case, and the other one is a reference to the next one, okay? And the last one on the list will often point to null. You often say this one points to null, and all you need is the start, and you can walk down this list by saying get the next one, get the next one, get the next one until the next one is null, and then you've traversed that list, okay? So that's what we call a linked list. And again, if you look at the Waterloo visualizer, it's really easy to see how this works when you visualize it in the Waterloo visualizer, so I strongly recommend that, okay? Now what we're going to do is create this little thing here. So this is a class. We're going to create linked list objects, okay? Each one object has two fields in it. One is the actual integer, and the other one is the reference to the next one. Int value, like that. And then the next one is going to be of the same type as itself. It's what we call a recursive data type, a type that refers to itself. It's a recursive data type. So next, okay? So that's all you need for your simple little linked list, is a value that's holding and a reference to the next one, okay? And then you need a constructor, int linked list, okay? And our constructor is going to just take a value, right? Like this, int value. So we make this one with a value 3 in it, or 4 in it, or whatever. And then he would just say this dot value, that is the value of this object, is equal to whatever was passed in. This dot value equals value, like that, okay? So we do this, and then we'll say, then we want to have a thing for adding to our linked list. We want to add something to the list, okay? So say void add, we're going to add a value to our linked list. I don't mean arithmetically add, I mean add a new value to our list, okay? Like that. So we're going to have our value here, we're going to add to the list, and then we'll say, what we need to do is to say, for the one that we already have, we want to add something to it. If the next one is equal to null, then we just create a new one and add it there. Otherwise, we recursively say, oh, the next one's not null. Okay, then go to the next one along and ask it to add it. And it goes on and eventually gets to the end of the list and it'll add a new one there. Okay, so if next equals null, then we say next equals new int linked list with value. Okay, so it's going to add that onto the list. Okay, otherwise we'll say next.add. We'll call add on the next one, because it's if we do have a neighbor, then we'll add it to that. Okay, so like this. So that's recursive. Okay. Oops, keyboard issues again. Okay, so we'll add it to next. All right, so that's our recursive linked list implementation. Now all we need to do is to have a way to represent the linked list. So let's do that. And the way we'll do that is with a toString. I didn't know IntelliJ would do that. There you go. I just typed the @ sign and did all that for me. Okay, so now we've got a toString method. And what we're going to do is we're going to say if our next is null, then it means we're at the end of the linked list. So it means we return the value with nothing after it. If next equals null, then we're at the end, so we don't need to do anything other than return the value. And we've got to turn that into a string, and the one way to do that is to do this, which forces Java to say, oh, okay, we're adding strings. That's string concatenation. Otherwise, we'll say else. We will return the value, that's whatever that we're containing, plus that with a comma, plus whatever comes next, and that will be recursive, right? Because next will be a linked list, and so it'll call its toString, and then it'll recursively print all the stuff out. If you didn't follow that, don't worry. Step through it with the Java Waterloo visualizer, and it should make sense. Now let's write ourselves a main method here. Then we're going to create ourselves a list. Int linked list list equals new int linked list 5. And there we go. We should now have ourselves a linked list with one node in it, which has the value 5. And print this out. We'll say like that. And then we've got the list like that. Okay, so let's just run this. And that'll be very unexciting. It should just print out 5. What are we doing here? Why can't we run this? Oh. My PSVM, I did too fast. PSVM like that. And it actually did set value. I don't know why it did that. IntelliJ just put all that other stuff there by accident. All right, so that's probably mistake number 5 for the day. That's not what I meant to do. So now I have a main method. So now I can actually run it, and that little icon there changed. Now I can run it, and there it is. So we've got a list with 5 in it. Fantastic. Pretty unexciting. We can add more stuff to the list. List.add, and we'll add 3. List.add. Oops, do it before the printout. Up here, we'll add these values in like this, and add in a few other values here like that. Save it, and pretty unexciting, but should print this list out. Okay, there it is. Okay, so that's our list. So far, nothing remarkable and nothing to do with generics yet. Okay, basically what we did is we just made ourselves a pickle truck. This is a linked list that can only do ints, okay? Which is like the pickle truck, a truck that can only carry pickles. Not useful. What we're going to do now, which won't take us very long, we'll do it in the next few minutes, is we're going to duplicate this and make a new version of this, which is generic. And we'll call it generic linked list. Like that, okay? And all I did there was I just copied the code, nothing more than that, okay? So now what we're going to do is we're going to give it a type parameter, which says we can specify which type this is. And the way you do that in Java is with these angle brackets, like this. There it is. And now instead of having an int value, it's going to have a value of type T. We haven't said what type T is. That's what's really interesting about it, okay? So we haven't said what type T is, okay? Now we've got to change this from being an int to being of type T. So now it says, okay, when we construct it, it's not going to take an int in anymore, not going to take in a pickle anymore. It's going to take in a generic thing, which is of type T, which is not yet specified. Okay. When we want to add something to our list, again, we don't add ints. Instead, we add type T. Okay. T is not specified. It's an abstract idea. It's a type parameter. Okay. For some as yet unspecified type called T. Okay. And then we go to toString. That all just works, luckily. Now what we need to do is we need to parameterize this and say integer. Okay, so now we've nailed down this to be of type integer. So we've got a generic linked list which happens to be of type integer. And I'm going to just, for convenience, yep. And if we run this, lo and behold, it should behave exactly like before. There it is. But what's different is that we can change that letter. Someone asked, does it have to be T? No, that could be Q, P, R, S, whatever. And later on semester, you'll see us use different letters. There's just a convention that we use T because it stands for type. It's the type. And in this case, it's integer, okay? But it's a generic type. It's a type parameter. And we just use T by convention, and it's short, okay? It's just a common practice to do that. Okay, I'll make this a little bit bigger so you can see this. Okay, there's our whole class there. We've made everything. All I did now is replicate this class here, but made it generic. So this is no longer like the pickle truck. It's a truck that can take anything. It's a container that can take anything. Now let's change this and refactor it to change its name just to make this easier. I'm going to call this an iList because it's an int list, like that. All right, great. Now we'll go and duplicate all this stuff here, and we'll make it take doubles. Let's change this to double. All right, and change this to be that dlist, like that, and change this to be a double, like that. Okay, and then what I'm going to do is I'm going to change all these things here to be dlist, and it's complaining because we're giving an int to a dlist. We need to make those doubles, and now it won't complain anymore, like that. And then we can do the same thing. So let's just do that. Let's just run this. I didn't type dlist here. That's why it printed the same thing twice. There we go. Let's run that again. Okay, perfect. And I can change this to be some other number. It doesn't have to be the exact same number, right? It could be anything, and it'll still work. So what we're doing here is we've now managed to reuse this code. This simple little piece of code here we wrote can now be reused with different types. This is the generic linked list instead of being a specific linked list that it can only handle integers. Now it is a generic linked list that can handle any type, which is really cool. And we can add in here the a string as well, right? We can do string and call it an S list, and we can put in here and then change this to S list, change that to S list, oops, and change these to strings. We could make it a string that happens to be the same number if we wanted to, like this. Or we can make it something else like foo, whatever. It's any old string, but they're all strings. That's the important part. And now we run this again. Okay, running it again, and there it is. And you see our strings, one is that, and another is a string that happens to look like a floating point number. Another is a string that happens to look like a floating point number, a double. And the other one is a string called foo. Okay, so that is generics. Generics are a very powerful idea. It allows us to write our code, instead of being specific to a particular type, we can use a type parameter, which is what that T is. We use that type parameter, and when we use the type parameter, we can then create one of these things here where we specify that type parameter, say, hey, we're going to do one with an integer, hey, we're going to do one with a double, hey, we're going to do one with a string. So now we're creating instances that reuse the exact same code, but with different types. Very powerful idea, okay? And yeah, there's a linked list type as well, which takes a parameterized element type, and we're going to dive into that deeply later in semester. Okay, yes, Angus has posted that on the chat there. We're going to dive into those in great detail, and in fact later in semester we're going to build our own implementation from scratch, okay, of a whole lot of container types, things like linked list, array lists, hash tables, hash maps and sets and so forth. And we'll be building those from first principles. Okay, so these are very important ideas that will get used later. And remember, the basic idea is we don't want pickle trucks, we want generic trucks. Even though pickle trucks are cute, they are expensive to make because you have to handcraft each one separately. Whereas if you do it this way, you can reuse the same stuff every time, which is a very powerful idea. Finally, and we have just enough time for our bio, and we have one of my favorite people. If you come to my office, right next to Robert Milner room, okay, right, I mentioned Robert Milner. He was the guy who invented ML, and we're going to do Milner later. Right next to Robert Milner room, there's a beautiful portrait of Robert Milner. Right next to him is this portrait here, which is a fantastic portrait of Bob Floyd. Bob Floyd was a total character. I never met him, I never knew him, but I've heard so much about him. What was so interesting about him was, well, he was apparently a character, as in an interesting guy. He was a child prodigy, as from what I understand, but he pioneered the idea of using mathematics, formal notions, formal reasoning to understand correctness of software. And that fed into the work that people like Milner did later, and it helped us build up some key foundations in software engineering, okay? And then, in terms of what a character he was, you can go and read a bunch of stuff about him, but he was famous for, apparently he'd carry a backgammon board with him. Like, you meet him in the airport lounge, he'd have a backgammon board, he'd bring it out and say, hey, you want a game? And he'd always win, right? He was very, very good at these games, and he'd play for money. What else did he do? Oh, he did many other things. One of them, if you look very closely at that picture, you probably can't see it over the video link, but that is actually a pixelated picture, right? It's made up of only two colors. Okay, it looks like it's got gray and shades of gray. That picture there does not have shades of gray in it. It's made up of exactly black and exactly white. Okay, now those of you who've looked at newspapers or any other print medium like that may have seen this before, where they make something that looks like it's got shades of color, where they actually use dots of a single color. And that process is called dithering. And one of the techniques we use in computer science for dithering is called Floyd-Steinberg dithering. And Bob Floyd invented that. And so that particular portrait of Floyd is dithered using Floyd-Steinberg dithering. And that one there, I actually got this portrait from the guy who originally got it, a guy called Don Knuth, who's another famous computer scientist. And this was done after Bob Floyd died. He died young. Sadly, he died of a degenerative brain disorder. And this was rendered using his own algorithm, so it's kind of a cute twist there. Anyway, another great person in computer science, Bob Floyd. And with that, we're done with the Monday lecture. Hang on, there's a couple of questions here. All right, yes, there's a picture there of a doubly linked list. The one I gave you is a singly linked list. We'll talk about doubly linked lists and singly linked lists later, but at the moment that's just the one I talked about was a singly linked list. Look, we've got like 2 minutes left. What I'm going to do is go to the course webpage and actually show you this stuff here. Generics, there we are. Generic linked list, fantastic. Let's go through this. Hopefully it'll wait, processing our code. Here we go. All right. It's building up the list bit by bit by bit. It'll take a while. There's a lot of steps in this. Okay, so I'm clicking really fast here to make this happen quickly. What it's doing, it's constructing an integer linked list. So there's the value, and there's the reference to the next thing in the list. Next, like this. And that's the value inside of it. That one's got a 5 inside of it, that's got a 3 inside of it, and that's got a 7 inside of it. We go like this, we keep going. And we're building up this linked list of integers. Okay? And you can see each one of these is what we call a box. And inside the box is a 5 and a reference to the next one, and a 3 and a reference to the next one, and a 7 and a reference to the next one. And here we're now building up a double linked list of doubles. And you see that it looks almost exactly the same, but the thing inside the box is not an integer but a double. Okay, and then finally, I guess we'll do strings. Yep, so there's an awful lot of steps in this example. By the way, you don't need to click like that. You can just use a slider, which is what I'll do. So it's a little less noisy. There you go. And finally, there you can see a set of strings. And so you've got the value here as a string type. And again, a reference to the next, next, next. And the last one on the list has null as the next. Null is the next. It tells us we're at the end. And you end up with, that's what you finish up with. Okay, so here you have 4 elements in the linked list where each one is an integer. 4 elements in the linked list where each one is a double, and 4 elements in the linked list where each one is a string. What's really cool about this, and the whole point of this lecture, is they're all using the same code, and it's generic code. Okay. With that, I'm going to finish up. Have a great week, and I'll catch you on Friday. Don't forget Friday guest lecture. Friday's the guest lecture, and I'll catch you then. All right. See you.